The purpose of this video is to help review different topics from chapters 1 through 3. So if you would go ahead and try each problem first, and then you can come back to the video and kind of fast forward to whatever explanations you might need or the answers or whatever, that's totally fine. But go ahead and try it first just to see, just assess yourself and see where you're at with each problem, and then come back to the video. So this problem for number 1 represents a piecewise function. So it's asking you to graph 3 different lines, but it doesn't want the entire line, it only wants pieces of each of them. So we want to graph the line y equals x, but only for the x values in between -2 and 2. And then we want to graph 2x, but only for everything less than -2, and 3x for everything greater than negative or +2. So we have kind of these boundary lines here. This is where we're chopping up our graph. So if we were to graph the normal line y equals x, our y-intercept is 0 and our slope is 1. So we would get something that looks like this, but we only want from -2 to 2. So that means we only want this middle portion here of that line. So we would go ahead and connect those ones, and on our endpoints, if it's just less than or greater than, you would use an open circle to show that 2 and -2 aren't actually part of that graph there for that line. If it were or equal to, you would then go ahead and make it a filled in circle. So for this next one, y equals 2x, we only want everything less than -2, which means we want everything on the left half of the graph from -2 to the left for forever. So my y-intercept would be 0, 0. My slope would normally be up and to the right, but I'm just going to extend it in the negative direction because that's the only half of the graph that I want in the first place. So on our boundary line here, it would be an open circle, and it would be only everything to the left of -2 for our x values. And our last one would be the line y equals 3x. Normally you would graph it at 0, 0 with a slope of 3, and you'd extend it both directions, but we only want everything for x values that are 2 or more. So therefore we only graph the right half of that, and then you can go back and erase anything that's not part of your graph. So that's what a piecewise function looks like. It looks like pieces of different functions put together on the same graph grid. Let's take a look at objective functions and maximization problems. So this jumps to chapter 3. So if you want to look back in your notes, this is in chapter 3. So you're going to be given different constraints. This represents a system of inequalities. So we are going to graph each of these different inequalities. So this first one here is x is greater than or equal to 0. So we have our x equals 0, and it would be everything to the right that's shaded. We have y is greater than or equal to 0, so we have y all the way across, and then everything above that's shaded. And then our last one would be x plus y is less than or equal to 3. So my y-intercept is 3, and my slope is -1. So we would have this line here, and as best as I can, there we go. Oh boy, I got off, but you get the idea. I'm going to go ahead and erase the shading. So what's happening here is we are being kept in the first quadrant with our first 2 constraints. So these first 2 here, x is greater than or 0 and y is greater than or equal to 0, means that our final answer has to be in this first quadrant. And so to figure out if we are looking at that small triangle or that unbounded shape to the upper right, we need to look at that last one. So we can test 0, 0. 0 is less than or equal to 3. And since 0, 0 works, it's on the shaded side. So for the green one, everything down here would be shaded. And what that means is that means our solution here is going to be this triangle shape. This is called your feasible region. And in order to find the maximums and minimums, if there are both a maximum and a minimum, we look at our feasible region and we identify all of the vertices. So the vertices of this feasible region would be 0, 0, 0, 3, and 3, 0. Once you have your vertices of your feasible region, you're going to plug in your x value and your y value into your objective function. So 4 times 0 plus 0 is 0. 4 times 0 plus 3 is 3. And 4 times 3 plus 0 is 12. Now, Since our region here is bounded, meaning I can trace all of the sides of this and see all of the points that are in my feasible region, that means you're going to have both your maximum and your min. If your feasible region had been the other one, the yellow portion over here, then you would say it would have a maximum or a minimum, and you'd have to test a bunch of values to figure out if your objective function is giving you larger numbers or smaller numbers than the ones that you have. So for this case of these numbers here, our maximum would be 12, and that would be at the point 3, 0. Our minimum is our smallest number, which is 0, and that occurs at the point 0, 0. Okay, let's go ahead and take a look at this system of equations. So we know how to solve this with matrices. We recently have done that, but we're going to go back to doing it by hand just to make sure we remember how to do that. So we're going to go ahead and label matrix A, B, and C. You're going to pick a variable that you want to eliminate. So it doesn't matter which one. I'm going to eliminate x. And I'm going to take equation A and equation C and use those to eliminate x because they're already set up nicely for that. When I eliminate x for those, I get negative 3y plus 3z equals negative 12. Then you're going to do the exact same thing. You're going to eliminate x, same variable once again, but you're going to have to pick two different equations. So for this one, I'm going to take a and b, but I'm going to have to take and multiply a by negative 2. And I would multiply b by 3 in order to make the elimination work. So we're going to go ahead and multiply everything in a by negative 2. And we're going to multiply everything in b by 3. And we're going to add them together. So we would end up getting 5y plus 5z equals 0. So now we can go ahead and use elimination or substitution. You're going to take your two resulting equations, this one, and you're going to solve for either x or y. Now for this one, only because I saw that y and z, we had the same coefficient here, I saw that if I moved the 5z over and then divided by 5, I would get y equals negative z. And so what I did is I actually used substitution for this one. I'm going to plug in negative z where I see that y. So this becomes positive 3z plus 3z equals negative 12, which then makes our z value negative 2. So if we have our coordinate points here, we know that z has to be negative 2, which means if I plug in negative 2 for z, I know that y has to be a positive 2. Once I know two of these, what I can do is I can go back to any equation. It truly does not matter which one. And you can say, I'm going to go ahead and solve for x by plugging in 2 for y and 2 for z. So we're going to end up getting 3x equals negative 3, and so therefore x would have to be negative 1. Once you get your answer, you can always check your answer by plugging in negative 1 for x in all of your equations, 2 for y in all of your equations, and negative 2 for z in all of your equations to see if you end up getting 3 true statements. Okay, so we're going to do a system of equations now where we have to set everything up. So this is a mixture problem. We have a cost per ounce for macadamia nuts, peanuts, and then cashews. We want a 20-ounce mixture. And so when we did this in class, we said you should have this big warning sign going off in your head for mixture problems. So we want a 20-ounce mixture, and we have the cost per ounce. So we're going to do 90 cents per macadamia nuts, 30 cents per peanuts, $1.30 per cashews. Let's do Z for that one. And overall, we have our price per different type of nut times how much of that nuts we're going to use. So we're going to use the price per ounce in our total mixture, but we have to multiply it by the total number of ounces. So that's what that mixture problem was. That's where you had to do the price times the amount. The combined weight of macadamia nuts and cashews, so macadamia nuts and cashews, is equal to the weight of the peanuts. So we have x plus z equals y. And we have two equations right now, and we need a third. So what happens with these mixture problems is that when we do our price times the amount, that's how we end up with our first equation. But the number of ounces is going to help us come up with the second equation. So we want 20 overall ounces, and we don't know how many x, y, or z ounces we would have for macadamia, peanuts, and cashews. So we would just use x plus y plus z equals 20 for our third equation. So at this point in time, if you need more practice with using elimination, feel free to solve this using elimination. Otherwise, you can practice solving this using your matrices. Either way, pause here if you haven't already tried this one and solve this equation, and then come back for the answer. So overall, we have 6 pounds of macadamia, 10 pounds of peanuts, and then 4 pounds of cashews. So thank you very much for listening. Let me know if you have any questions on any of the different topics.